Question 2, we're looking at reflection. A man sees his image formed in a flat mirror. One of the properties of the image produced by a flat mirror is lateral inversion. Describe two other properties of the image produced by a flat mirror. Okay, well, there's a number of different ones. If we're talking about the image, we would say the image is virtual. That means it's not made up of real light rays. We could talk about the size of the object and the size compared to the size of the image, or the magnification. So magnification, and we would say that magnification equals 1 because the image is the same size as the object, and it's a ratio of 1 over the other. I don't know if that's at level 1, but it still is magnification of equaling 1. You can also add that the image is upright. So that's not upside down, it's not inverted. We've already said it's virtual. What else? I guess we're going with that magnification being 1. The distance from the image, that's the image, and the object, it's going to be the same distance apart. So that's also another, I think that's more than enough. Okay, part 2. A man holds the card shown in front of the mirror. Write the word he sees in the mirror. Oh my goodness, this is going to be tricky to see. This is a lateral inversion thing. It might be easier for you to draw this left-handed and try, but anyway, the W is going to be on the right-hand side rather than the left, because that's that lateral inversion. Oh, this is nice, they're all capitals. So they're actually symmetrical for most of these words. W, A, B. Now the E, instead of pointing that way, it's just going to point the other way. So it's going to be E, and our S, instead of curling from the right-hand side to the left, it's going to curl from the left-hand side to the right. Oh, that's a tricky one. Should look a bit strange. That's what you'd see in any case. Moving down. B. We've got the diagrams show similar sets of parallel rays of light reflecting off two surfaces made from the same material. So surface A is flat, surface B is not perfectly flat. So anyway, part 1. Describe how the two reflections are different. Depending how we want to look at it, surface A is regular, so A is regular, predictable, nice, going with that surface pattern. B is irregular. Technical terminology for being a non-regular surface, or uneven surface, or flat surface, or something like that. We could describe the reflected rays for A being parallel reflected, and B not parallel. That's another way of putting it. We could see talk about surface A providing a clear image. Okay, so if it's a mirror, it might not be a mirror, it could just be some any coloured paper or anything flat. But if it's a mirror, then surface A would produce a nice clear image, and surface B would produce, I guess, a scattered image or a bit muddled. Depending how bad this surface is, you would get a bit of a muddled and watery kind of look, perhaps. What else could you say? I guess you could say that the angle of angle of incidence equals the angle of reflection nicely. So I guess this is explaining, yeah, we'll explain why. The angle of incidence always equals the angle of reflection for both of these, so that's a good contrast comparison. We've been contrasting so far, which is part of that whole difference thing. But what that produces in each case is, with this one you can see we've got these nice parallel lines coming through, whereas we've got boom, 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 3 scattered lights because of the angle of incidence. So you could talk about that as well. Okay, part 2. Or maybe that's explain why the same set of parallel rays reflect differently. Okay, we just explained that. Okay, that's me jumping ahead. Because the angle of incidence must equal the angle of reflection, and the uneven surface reflects therefore at different directions, even though that angle of incidence is equal to the angle of reflection. Okay, moving on. Whew. Tough doing this stuff on the fly sometimes, but who has time to prepare? Two adjoining walls of a small bathroom are lined with mirrors as shown in the diagram below. Uh-oh. Explain how the mirror walls make the room appear larger than it really is. Okay, it's not as bad as I thought. Thought they were going to say, let's have an object in the middle here and draw some ray diagrams to show how they're reflected in the mirrors. But whew, okay, now instinctively you know that you're going to get a more of a sense of space, because everything that's in the room is going to be reflected on the other side of the mirror in both cases. So you get this heightened sense of space. That's very clear. Now, oh, excuse me, I'm going to sneeze. Okay, that sneeze passed. Where were we? So, yeah, I think I thought that was a bedroom, but it's a bathroom anyway. It's only two of the adjoining walls. If you had a mirror here, you had the bathroom floor in the middle, and then you had another mirror over here, that wouldn't be adjoining, but that would create an enormous sense of space, as the light rays can kind of keep bouncing between the two and create this enormous sense of space further, because you've got the space of this mirror reflected in this mirror, which all that space then is reflected back over here, and it infinitely goes back down. But these two are joining each other, so they're not reflecting each other. What you would see is, let's see if we can draw a rough sketch. There'd be a wall in place here, and that wall would be reflected equal distance apart back here. So you'd have that extra sense of depth to account for, or from that wall being seen in the mirror an equal distance away. Okay, you get the idea. So in fact, you've got twice the distance to what there really is in the room is what it looks like. Okay, moving on. D, a girl sitting on one end of a glass top table, a burning candle is placed at the opposite end. She sees the light from the candle reflected by the glass tabletop. Okay. Draw a ray diagram to show how the girl sees the image of the candle produced by the glass top of the table. On your diagram, show the size, the correct position, and orientation of the image as seen by the girl. Okay. This is going to be a tricky one, because you have to conceive of a whole kind of picture of what's going on. Oh, excuse me. Now, something that's important to note is that, is that the light rays, people often forget that the light rays don't come out of people's eyes. So they have this idea of, here's a person looking, and they're seeing an object, so the light rays are coming out of their eyes to the object. Nope, it doesn't work that way. Remember, the object gives off light or reflects light from the sun or whatever sources of light there are. That light then goes into our eyes in that direction, and then it's registered. So anyway, let's have a look at this diagram and see what we can do to draw the image of the candle produced by the glass top on the table. Alright, let's go for red. So the first thing that you'd probably want to do is imagine what you would see. And this one could be helpful if you've got a mirrored surface or something else reflective, which might be a cell phone screen. And you can just stick your pen on the cell phone screen, probably not so that it draws on it, and you can see the image you're expecting. What you would actually expect is your candle down here. I'm just going to draw an arrow, not the actual candle, and with the head of the candle pointed down. So how do we arrive at that? Let's draw our dotted line. There's nowhere for the bottom to reflect to. It'll go straight along the surface. Okay, so that's an important thing to note. But if we take the top, that has to hit somewhere in the middle and then reflect up to this girl's eyes. Okay, drawing the arrows to show the direction, because remember they're going into the eyes, not out of. And then the next part is to show where that would appear to come from, which is down here. That's the top of the candle. Okay, you could actually do this with a number of different rays. and each of them would be slightly different. Let me see if I can get this right. If you have a ray that's coming from halfway along here, and yeah, it's when it hits this same point. See if this will work. This could be a little bit of a trick. That, as it stands, should be enough for your result. But let's just push it a little bit. See what we get. So we should have another ray coming in here, and it'll reflect according to the equal angle law. Okay, so that's cool. It's spreading. These two rays are spreading out here and here. That second ray will appear to come from, yes, perfect, halfway through, which is what you would expect. So you'd only need one really, but. And then the very bottom ray, just as I was saying before, there's a zero, or it's at the flat surface, so maybe it's a 90-degree angle of incidence. So it's going to go straight along, or the angle of reflection is 90 degrees. Now here is a really interesting thing. This is not part of the question, but it's not actually reflecting off the top surface of the glass. Here's your candle, just drawn as an object, and it's not reflecting off the top surface of the glass. It can't, because it would refract instead. It has to travel inside. What is really happening is that that first light ray is coming down, it's bending towards the normal, and then this angle here of incidence is greater than the angle of the critical angle, that is. So we'll have reflection on the bottom surface, because remember the refractive index here of the glass is greater than the refractive index of the air, and this is the air under here, and this is air on the top. So you can't get reflection going from a low, which is about 1.00 refractive index, to a high, which is about say 1.5 for glass approximately. So it's going to reflect off that bottom surface, total internal reflection, and then bending away from the normal again. But because the glass is so thin, so this distance of thickness here, we can approximate it to be zero, and we can approximate the actual angle or plane of reflection in the middle, and just say that it's reflected off that point. Okay, if you didn't follow that, don't worry, it's just useful information for background.